Hi everyone, in this lecture 9, we will check the simulation result against analytic expressions. First, we consider the MOS equation. What is the MOS equation? The MOS equation is so simple and straightforward. Consider the electrostatic potential phi. Also, consider 3 points R1, R2, and R3. Then, quite obviously, the potential difference between R3 and R1 can be divided into two terms. Difference between R3 and R2. Difference between R2 and R1. That's it. It is an identity. Yes, it is an identity, and any position can be selected as R1, R2, or R3. However, in the MOS equation, some special points are taken into account: substrate, interface, and gate. Then we know that the total potential difference between the gate and substrate contacts can be written as a sum of the oxide potential and the silicon potential. Let us introduce the x-coordinate. X equal to minus Tox represents the gate contact. The electrostatic potential can be expressed as Vg minus phi ms. Here, phi ms is the work function difference between the gate metal and the reference semiconductor. The interface is located at x equal to 0. Finally, we assume a deep substrate. The substrate can be found at an infinitely large x value. Of course, the potential is determined by the acceptor density. It means that only the electrostatic potential at the interface is unknown. Let's write equations. Using the symbols in the previous slide, the identity becomes this form. Here, oxide potential Vox represents the potential difference between the gate contact and the interface. In order to simplify the notation, we introduce two quantities. One is flat band voltage. When the gate voltage is the flat band voltage, the band profiles inside the semiconductor region become flat. Another one is the surface potential. Since the interface is located at x equal to 0, phi 0 is the surface potential. However, in many cases, we take the substrate potential as a reference. Therefore, when you find a surface potential in textbooks, maybe it is the surface potential minus the substrate potential. With these quantities, we have quite a simple expression. Although written in a different form, up to now, the message is simple. The potential is divided into two parts, one for the oxide region, another one for silicon region. Now we make an important observation. The oxide potential is related with the charge. When the capacitor per area is denoted as Cox, we have a simple relation between the oxide potential and the integrated charge in the silicon region. Note that Q sub S and Cox are quantities per area. Then, instead of the oxide potential, we have an equation related with the semiconductor charge. It is the MOS equation. It is an exact relation, however, Q sub S and phi sub S are unknown. We need additional relation for them. Unfortunately, the relation between Q sub S and phi sub S is not generally available. Only for some special cases we can find analytic expressions. One lucky example is the planar MOS considered in this lecture. Let's derive the exact relation. We must solve the nonlinear Poisson equation. In the 1D structure, it is written this form. The trick is so simple. Integrating the Poisson equation itself does not give us additional information. Instead of that, we first multiply d phi over dx. It is minus 1 times the electric field. After simple manipulation, we integrate the Poisson equation multiplied with the weighting factor over the semiconductor region. In our example, the integration is performed from 0 to infinity. It gives us this result. Well, it looks quite complicated, but we will arrange it. First of all, it is noted that the electric field vanishes at the substrate. In other words, d phi over dx equal to 0 at x equal to infinity. Also, we introduce carrier densities in the substrate. The hole density at the substrate is denoted as P sub P naught. It is very close to the accepted doping density. The electron density at the substrate is denoted as N sub P naught. It is a really small number. With these two densities, we can simplify the equation. The resultant equation contains phi 0 minus phi infinity. What is it? It is the surface potential phi sub s. So we can obtain a greatly simplified equation. It looks much better than before. As a result, we find this. Square of the surface electric field is given as this form. Once again, the surface electric field is related with the semiconductor charge. By taking the square root, we finally get an exact relation between Q sub s and phi sub s. Yes, it is exact, but it is noted that such an exact relation cannot be obtained for general cases. By solving the MOS equation together with this relation, we can accurately get the semiconductor charge Q sub s and the surface potential phi sub s. From the device simulation, you have numerical result. In this lecture, just use the solutions to check the analytic expressions. Q sub s can be easily obtained by integrating the electron density and the hole density. Of course, we need phi 0 and phi infinity to calculate the surface potential. That's it for this lecture 9. We can solve the MOS system in a numerical way. Also, we can derive the MOS equation in an analytic way. Now, it is time to move to the transistor. In the next lecture, we will start simulating the MOSFET. Thank you and see you later.